Okay, so thanks for having me. This project is something that grew out of my collaborations with Hugo and the team he led at IBM. And it has to do with the I/O efficiency that he mentioned several times in his talk. And I'll get to that after some context. So I'll start with my view on searchable encryption and how it might be used. So when we outsource data just as users to services like Google Drive, we might not think about this, but it is amazingly nice that you can just find the stuff you want very quickly by typing in a keyword and getting only those documents, even if you have a ton of data in that service. So here I have 6 gigabytes of documents in my Google Drive, and I just get it instantly without thinking about it. But when you take a closer look at these services, it's becoming more clear that we should think of these providers as adversaries or as adversarial. We have hackers threatening our security. Insiders of the companies, and even government surveillance is something we should think about before we put data in the cloud. And one way to do this is end-to-end encryption, meaning you just encrypt in the browser, encrypt in the tool on the client side, and then upload it, and you don't tell the cloud the key. The problem, from my point of view in this talk, is that we can't search this data anymore, at least naively. This is the problem that I think every talk has mentioned so far. But if you just try and naively put a layer of encryption there, the privacy or security goals of traditional encryption are in tension with this. We just can't search out of the box. And so let's think about how you might, okay, I have a new slide here that wasn't from before, but this isn't just a theoretical curiosity of speculating how this might be done. There are actually a bunch of services available online where you can go download an iPhone app or log in on their website and create an account. And if you use these, you really can't search, and it's really a pain in the ass. So I tried SpiderOak and one of these other services, and I put a couple of thousand PDFs on there. And if you want to access them from your phone, it's really cumbersome. And I think that it's quite plausible that that's one of the features that's holding these companies back from deploying end-to-end encryption more widely. But let's think about, if you are a programmer or a security-aware industry person and you are trying to solve this problem, there are some easy ways that you might try and do it. So one way is to just take your encrypted records. They're encrypted in good old traditional encryption, but also just keep some index information around like you would for a plain text system and just don't encrypt that. So now you can search using this auxiliary information. So the resolution is lower than I was expecting on this projector. But what you do is you build an inverted index. So the rows are labeled by the keywords that you might want to search for. And then you just list all of the documents where that keyword appears. So this is how plain text searching generally works when you have time to index. And so now when you want to search, the server can return the encrypted documents without decrypting them. Unfortunately, you just look at this auxiliary information is going to tell you a lot about what's in these documents. And there's even been work by natural language processing people on piecing together the documents from this. So taking these words and putting them back in order and figuring out what the documents might have been. And they were successful on tweet length records. It's unclear about longer documents. So here's another solution to the problem, is to just keep that auxiliary information, the same sort of inverted index on the client side, and use that for searching. So now when you want to search for meeting, you just do the search yourself, and you just request the documents that you're interested in. And the server can give them back to you. Unfortunately, when you generate an index like this, it's often as large as the text you started with. So this obviates the whole point of outsourcing in a lot of contexts. And even this isn't perfect. We've heard a lot about access patterns so far today. So is the server still going to see, or this provider still going to see that you go for 4, 9, 37, and then tomorrow you get 9 and 37, and so on. And he might mount in a statistical attack anyway. And so searchable encryption, as we've been talking about it, is something I'm going to formalize here, is a way to get some better trade-offs between these various trivial solutions. And so I'm going to think of searchable encryption as 3 pieces. So the first part is encrypted index generation, where you start with a bunch of documents on the client side and a key, and then you end up transferring them to a cloud provider encrypted with some auxiliary info that's either encrypted or not, structured or not, and so on. The second piece is then a search protocol that allows this client to say, I want all the documents that have California, and then somehow interact with the cloud provider to get those documents, and then decrypt them locally. And finally, and this won't be too relevant for this talk, but it will be perhaps for Tom's talk in the afternoon, we want to update this stuff. So if you think of using this for your email or something, you need to add stuff to this repository. And so we're going to have an update protocol where a client's holding onto a record that that it's encrypted and then wants to somehow add it to this repository and update the helper information. And the idea is that this should still work. If I search for a keyword that appears in that new document, it should get returned in the search. And so here's a very simple searchable encryption scheme according to my rules. Very leaky, but better one that has been used in practice, at least in several places I've seen. So you can go ahead and generate this inverted index, and then just hash the keywords. Use a PRF. A PRF is a keyed uninvertible hash function, if you haven't seen those before. And then just upload this index to the server. So you've at least hidden the plain text words from the server. And then you just save the PRF key that you used to generate that. The search protocol is now totally trivial. You just send the thing you're after, the label for that row, and then the server can download it. The nice thing is that it's also really easy to update this. You can just recompute where, if you want to add document number 99, you just tell the server which rows to put 99 in. Good. So this has also all sorts of leakage problems. Again, so Tom is going to give a talk this afternoon about just how secure this sort of thing might be, and so I won't say too much more about that. But it seems like a good idea to just encrypt these rows and hide those also from the server. So the nice thing now is that if you're, so what I mean is you derive a per row key and you encrypt that row under that key and you keep it hidden. And the nice thing is that a server who just gets this blob really can't tell very much about what it might represent, what's in the documents. It requires more modification to the server than the other schemes I was outlining, which is why this isn't always done. And so in this talk, and in Hugo's talk buried deep as a low-level detail, was that we want to hide even more than this. Oh, so that's what searching looks like. You just uncover the row for the server, so he sees the numbers. In this talk, and in Hugo's talk, something that was buried in there is that we also want to hide a little more. We'd like to try and hide the lengths of these rows if at all possible. And the idea is maybe by looking at these rows over time, just the lengths, the server can maybe start to think about what kind of index is this? What is this index representing? And pictorially, I mean, we'd rather not store this kind of structured table that it can learn from. We'd rather just have this blob that to it is unintelligible and it doesn't say anything about the lengths. And so the searches should not reveal anything more than what they have to, just like lifting the cover off the row to tell you the numbers. I'm not going to try and formally define this because my short talk is even shorter now because I'm up against lunch. I'm not going to mess with that. But I'll tell you a simple construction, and you'll hopefully get the idea of how you might hide these lengths. Anyway. So from there, this is actually a paraphrase of a quote from our collaboration at IBM. When we just opened up the literature and realized that SSE was the right tool for the job, kind of looking at it, the thing was asymptotically optimal, but it was unusably slow for large indexes. So these guys were thinking of a 10 terabyte index. And the point that they were making is that the runtime bottleneck was not in exponentiations or AES or something like that. It was in how the disk was being used when you tried to use this length hiding searchable encryption thing. And so here's what was going on. We think of this, we have this kind of unintelligible blob that we've given to the cloud provider, and now the client wants to execute a search for a keyword. He interacts in the protocol, sending this little token. And the way these systems were designed, the cloud provider would go and touch one completely random, unpredictable part of memory per document that it needs to return. I'm using this term posting from the information retrieval literature. That just means one of those numbers from a row in that index, so a posting. So if I needed to return 4 documents, just when I'm touching the index, before I even go get the documents, I have to do 1 disk seek per that, so 4 disk seeks to get 4 results out. And each time I'm seeking, I'm only reading off a few bytes out of this massive database. And so this is very wasteful in terms of disk utilization. And this should, of course, be compared to plain text searching, where any reasonable system would just put those rows together so that when it's time to read row 3, you just read it and you're done. So this was kind of a problem where I didn't know much about this. So I looked around and I found something called I/O theory, which is not, it's I with a slash, not I/O like we think of it today. And so there's an entire theory of how to design algorithms to use disks well. And the idea roughly is that you just ignore everything about the algorithm except how many blocks of data moves back and forth from the disk. And, there's an entire sub-area of theory, and it's a neat area called IO theory. The Vitter textbook is a great place to start. And the nice thing about that this area for us is that we have lots of optimal results. Once you ignore fuzzy things like runtime and you focus on disk blocks moving back and forth, you can prove optimality results for algorithms. You could say this is the best possible algorithm for this job in terms of disk blocks moving back and forth, in the same way that we have sorting lower bounds, like an n log n for sorting. And so finally, I could say what we do in this work. We started a study of I/O efficiency and security, so the cryptographic security as we define it in theory literature. And the main result I'm going to try and sketch in the rest of the talk is an unconditional lower bound on searchable encryption. So we're going to say that in some sense, like we started with this intuition, that in some sense that jumping around on the disk was unavoidable, and we basically could see that it was hopeless to fix it. And so this project is about making that intuition formal and putting constants on it and understanding it and hopefully exporting this idea somewhere else. And the proof technique for this lower bound is completely different from the optimality results I said before. I'll get back to that. And we also give a construction. I'll state its parameters, but I don't have time to get into it in this talk. Okay, so here's what our lower bound looks like in a very, at a very high level, and I'll formalize each of these points in a second. It says that if you design one of these searchable encryption schemes that hide the lengths in these rows, it has to have one of these three drawbacks. Either you've created a very large encrypted index, so you've done a ton of padding on it in order to try and get some locality, or you're doing like what the existing schemes were doing, which was jumping around in memory in a highly non-local, unpredictable fashion. Or the third option, which nobody was really considering in practice, is you're just reading a lot of extra memory to make it local by just actually reading the gaps in between the things you're jumping to. And so this is an unconditional thing. I'm not assuming complexity assumptions. It's just a feature of you have to do this or you're insecure. And so we're not making any assumptions about how the schemes work. So this inverted index stuff is really the intuition, but we could think of any scheme that does it using any exotic data structure. And as I alluded to before, it's a different type of I/O lower bound. So instead of saying if you are too local, then you can't be correct, which is like what the existing lower bounds say. We say if you're too local, then you can't be secure, then there's an attack. Okay? So I want to formalize these three measurements because like coming up with that was new ground. Yeah.
So the I/O lower bounds are for things like sorting, computation.
Exactly. Yeah.
The lower bound is for search, right? It's for a weaker task, but you want security.
Yeah. Good point. So they give lower bounds like for a dictionary data structure that take like a key value store, and that's essentially what searchable encryption is in this formalization. So. Yeah. Okay. So again, I want this lower bound to apply to any construction. I don't want to make any assumptions about how it works. But I could say this, that no matter what searchable encryption we think of, we can view it this way as touching contiguous locations of memory in a sequence and then outputting its answer. Okay, maybe it does something trivial like reading the whole thing, but we can always view it this way and phrase it that way. So. So we're going to measure how it uses the memory in these three very coarse ways that I'm going to be precise about now. The encrypted index size is simple. It's just if we start with an inverted index that has n postings, meaning n total numbers there, and if you sum up the size of all these rows, then you get some blow up in the encrypted index size by some number. Next is the locality, which means the number of contiguous regions touched during the execution of a search protocol. So if we think this thing, we'll think of it as depending on the total size of the index and also the number of results that.
I didn't understand what is the number of postings? What is postings?
On the previous thing?
Yes.
Yeah, sorry. I meant to change my slides to get rid of the technical term postings. I just mean if you add up the links of all these rows, that's n.
So you are assuming something about how the scheme, like you're assuming that the scheme knows in advance all the terms that could ever be searched.
Yeah. I guess that is an assumption and just baked into the primitive. Yeah, I guess I am making a lot of assumptions by defining a primitive, but once the primitive is defined, I'm not going to assume how the goal is accomplished inside the algorithms. But yeah, I'm very much assuming that it's just like a row lookup data structure type thing at some intuitive level.
So it would not support searching for a new word that was not known in pre-processing.
Yeah, yeah. Yeah, it's just the way the way I want to define the primitive, which I wasn't careful about at all. Yeah, hides that assumption. Okay. So the three measures, the first is how much bigger the index is from what you started with. The second is how many contiguous regions you touch when you want to turn out a search. So if we want to execute a search that pulls out 4 documents, we could think of, said maybe the scheme touches 4 contiguous regions in memory. Maybe it only touches 1, or maybe it touches even more than 4. Okay. And finally, this is the more, if there's any controversy in these measurements, this is the one where we kind of made something up that worked, but is not really what we wanted. But we want to measure in some sense, reading a lot of extra memory. And so we looked at something called read overlaps, which I'm going to informally define as the amount of memory that's touched memory. Yeah, that's an awkward wording of that, but it's the amount of memory that any 2 searches will overlap on when they're executing on the server over time. And so, for example, what I mean is that this is the encrypted index laid out linearly in memory. We search for 2 words, and then a third word, where I'm talking about the size of this orange region, so the sum of that overlap. And the amount of overlap is just saying what's the worst case this could happen between any 2 searches, or for any search and all the other searches. And the intuition, at least my intuition, is that if you're overlapping a lot, then information theoretically must be reading some useless bits when you're doing the search. I never really formalized that. I conjecture that it's possible, but for some reason we didn't get it done. But we do know that the existing constructions have very small overlap. They sort of will touch a hash table at the top and overlap in some constant amount of bits and then go get the real results somewhere. Okay. So now our more carefully stated lower bound says the following, that if you have a secure scheme that's hiding the length, you can't have a linear size index with constant locality and constant overlap between the searches. In the paper, we give a trade-off. There's actually formulas that say you have to satisfy this equation with these 3 things. Yeah?
Sorry, some searches should have more than a constant overlap. So you're just talking on.
So you mean because they return the same documents?
Yeah.
So if you do that, you're not going to be secure according to the definition, or if you do that naively, you're not going to be secure according to the definition. Okay. So I'm sort of thinking of this stuff in a worst case sense. Like you still have to work even on indices where the same document just never appears anywhere else, and so you won't have any overlaps. But okay. Okay, so of course this isn't like a totally end of story negative result. Of course, Hugo's project still succeeded beautifully. And the idea is you just give up on security as we've defined it. You find another satisfactory notion of security and you hope that that's good enough in practice. But I stress that we're studying a definition that existed in the literature for 10 years or something like that. So it's still an interesting question to ask even though we circumvented it. Is that 10? But I want to talk about Columbia a little bit. Can I have? Okay, that's good. I don't have a super technical back end of this talk or something. I'll just really sketch what we do at a high level. I will say that the literature looks like this. So our lower bound says you either have to blow up the index, the overlap, or the locality, as it's indicated. This work by Kurdmola, Garay, Kamar, and Ostrovsky, which really laid out the type of definitions that we're working with here, settled on bad locality. So they would jump around once in memory per posting they needed to pull out. Another work of Chase and Kamara, while doing other stuff, pointed out if you're happy with quadratic padding, you can have perfect locality. You basically make those, you just hide the rows by making them all really big. Hide the links of the rows by making them all really big. Nobody ever wrote this down, but you can get a local scheme that just reads the entire block of memory. That's one contiguous region of memory, and it does something trivial, so you give up on overlap. So this sort of tells us that our lower bound is on the right track. In the paper, we give an intermediate point between these things with logarithmic locality and overlap, and then a subquadratic index size, so in login.
So, and the security here is only for the query, right?
It's the CGKO type of thing, like with the leakage. And what do you mean by query?
You're not protecting the data, you're protecting the query, right?
We want to protect both as much as possible. There's still this semantic leakage from the search. I'm not sure what.
Can you show your theorem again? Sorry.
Oh.
No length hiding.
Yeah, I'm being really fast and loose with definitions, which maybe was a mistake. But since it was a short talk, I wanted to. But yeah, I just mean the CGKO definition there. Okay. So in the time that's left, I'm just going to sketch one of these linked hiding constructions and why you can't localize it, and then very briefly say what this lower bound looks. So the lower bound's an attack, so we'll give the attack there. So here's the construction. This is roughly the construction from CGKO. They want to build a searchable encryption scheme. So let's just take the inverted index as input, and the first thing they did was derive a per row, per term, whatever, key, and then encrypt each of those individual postings separately. And then you have a Columbia key, big key, and so on. And then now you have these things. You're going to arrange them, and you just put them randomly in an array. So I'm keeping track of the colors to associate them. Sorry, Hugo. Here's some help. There's the purple ones. So the idea is that you just put them in there, kind of munging up the links and how they're related, and then you also encrypt pointers between the related ciphertexts, and then that's the whole thing. That's the encrypted index. Actually, there are some details that I'm cheating on, but it's something like that. And now, if you want to search, it's pretty intuitive. You just somehow you give the server the decryption key for that list, and then you somehow help them find the start of the list, which they do in the paper. There's another data structure there. And then the server does the obvious thing. You'll jump around in memory reading those things until it has all of the results. And to think about it in our terms for memory utilization, the index size is linear, but we're jumping around once in the memory per search result, so that's O of R locality. And then the read overlaps are constant because of that other thing, but they're essentially zero here. You're not reading common memory between the searches. Okay, so what would happen if we tried to make this thing local? Well, there's good reason why they didn't do it, but here's what you would do. You would just put them in memory, maybe like this. And since we're using good encryption, it doesn't actually reveal this. So everybody's colorblind when you use encryption. You can't tell the association between these things when you're just holding the index. The problem is when you start executing searches. Say if search one touches this region and another search touches this region, and then we know that, I learned maybe it doesn't sound dangerous, but it's not allowed in the definition. If I know how the scheme works and I know that these regions were touched, then I know that these 7 remaining parts of memory don't correspond to the same row of your original inverted index. I've learned that now there are at least 2 rows with some size characteristics, and that's why they had to sprinkle everything in memory to hide them. Okay? All right. So here, let's skip the restatement of that. So our proof approach now for the lower bound, saying that this sort of behavior is inherent, is to just do a proof by contradiction. Suppose you have a scheme that satisfies all 3. We'll show it's not secure. And we're going to design an attack. And this attack is going to look at what's going on with the memory access pattern of the algorithm and then output a guess of something that's going on. It'll do something bad. Okay, and then the special case I can get through, hopefully in this talk, is a very weak version of the lower bound. Let's just show that if you have a secure searchable encryption scheme, that it's exactly one local. It just reads one region of memory and has 0 overlap, so it never reads the same. Okay, I think we have time. Okay, then if you do that, then you have to have at least 50% blow up over the original encrypted index. So if your original encrypted index is 10 terabytes, you have to use at least an extra 5 terabytes. So this is somewhat interesting to know in the high end of scaling. And that's a statement. And so in the paper, we make it much more complicated and improve it to the bound that I had up front. So here's what the attack is going to look like. We're going to make two indices that look very, very different, and then try and tell them apart. So the first index is just going to be populated with one document, or each row is just going to have one random document identifier pointing to it. The other index is going to have one of these guys that matches a single document, and then another one that matches a ton of documents. And we're going to try and tell which of these two were encrypted. And what we're going to do is say after a search for the first one, the little one in either index, we're going to guess which of the two was encrypted by watching what happens. And so here's the intuition. It's to think about what would be read during each of those searches for each of those rows in the two cases. So if the one with all of the little rows was encrypted, then the possible regions that would be read, subject to our assumptions, look like this. They're somewhere in memory, and they're each one little block, because it's one local and zero overlap. Now, the other one would have one of these little blocks, and then a huge block for that huge row. It has to be somewhere, according to our assumptions. Okay, but they're not actually read. This is just what would be read. And if you think about what happens if I0 is encrypted and that W1 is searched for versus if I1 is encrypted and that little W1 is searched for. And so what's going to I got out of order here. If I0 is encrypted, then one of these, it essentially is one of these is chosen at random. So it's a pseudo-random read somewhere in this memory. But if I1 was encrypted, we're always going to hit that little block up there. Wherever it is, we're just going to find it. And our observations, or our proof is finished with two simple observations. So if I1 was encrypted, then we're always going to hit this one. And there's always going to be a room for the big block somewhere on either side of it, just based on our locality assumptions. But I claim that if the other one was encrypted, then there's a reasonable chance, a 1 over polynomial chance, that it won't happen, that there's a large block that fits on either side of it. So I say with some good probability, there will be a read in the middle that makes things overlap. And so this is intuitively pretty simple if you think about it for a minute. It's where the 1.5 comes in now. By pigeonhole, one of these guys has to be close to the middle, because you could like pack them all close to the edges, and then they take up too much room. And that's really the intuition for how we get started in our proof. The attack now just checks, did this happen? Like, I see how the search executes, I see how the memory's touched, and then I say, is there room for one of those large blocks left or not? So it's the same sort of attack from the colors and the blocks before. Okay? So I don't have time to go into it, and I don't have slides to go into it either. But we did quite a bit of work to push this to the full lower bound. Just to show you a picture of what the lower bound looks like, we have a ladder of rows in these more complicated indices where we're eventually going to hunt for a big list. Does it fit at the end or not after making a bunch of queries? And the attack is a kind of an iterated version of the thing I was describing before, where, let's just end this. We're going to start with memory unlocked. We're going to look at where a bunch of small lists touch memory. They'll be like that. So we prove a condition that says they're going to be close together pretty often. And we know that big intervals can't fit between them, so we can just mark off that memory. Then we're going to reach slightly larger intervals, and they're going to be pseudorandom, and we can mark off the space in between them where bigger things don't fit. And we keep doing this until we've queried all the stuff we need to, and then we conclude either there's this huge spot left where that big list must be hiding from the bottom row, or not. And then we can distinguish which of the two was encrypted. Okay, so I'll leave this conclusion slide up rather than reading it out so that we can all go to lunch. Thanks.